Hello and welcome everyone to the Meyer Sound MAPP 3D webinar presented by TC Furlong. We're happy that everyone can be here with us today. Before we get started, I do have some brief introductions. First off, I am Brian Gran with the TC Furlong sales and marketing team. For those unfamiliar with TC Furlong, we're a live sound company based in the Chicago area. We specialize in pro audio equipment sales and rentals, live event productions, and specialty services, including loudspeaker system design and alignment, RF coordination, and repair services. While we are authorized dealers for many brands and have a lot of items in our rental stock, we've had a special relationship with Meyer Sound for many years now, and we're excited about the new tools available with MAPP 3D. All right, so before we jump into it, some housekeeping. We are recording today's webinar, and we plan to be posting that to our YouTube page within the next week or so. We'll make sure to follow up with a link to that video once it's posted to everyone that's here today. Also, we're going to be using the Q&A section in Zoom to ask questions during today's webinar. We have a designated Q&A time at the end of the event. But please ask questions as we go. We'll be able to answer what we can kind of over the course of the event as well. All right, so today we are joined by Alex Harbaugh with the Design Service Supervisor with Meyer Sound. Alex, how are you today?
I'm doing good. Thanks for having me.
That's great. All right, so we can jump right into it here. First off, I will say we're assuming a entry-level understanding of MAPP and loudspeaker system design software.
All right, can you guys see my screen?
Yep, looks good.
All righty. Okay, so yeah, as Brian said, we're gonna do a basic look at MAPP 3D, assuming that there is a basic understanding of loudspeaker deployment and modeling. This is kind of what I call my high school level of MAPP 3D training. So if you can see my window, you'll see the basic default MAPP window. And I have a generic amphitheater that we can bring in from a SketchUp file. So let's import that SketchUp file so we have some architecture to look at. I'm going to go to File, Import, and SketchUp. And right here, I'm going to bring this file in. SketchUp has units built into the file format, so I'm just going to import it. It will tell me that part of the model is outside of the limits here, but that's fine. That's a lot of upstage stuff that I don't care about. So I've successfully imported my 3D SketchUp file, as we can see here. All righty. So first thing to say about importing DXFs or SketchUp files are layers come in with those models. So if I go over to my Layers tab on the right, I can see all the layers that came in with that SketchUp file. So to make things a little more clear to see what's happening at the listener level, I'm just going to hide the shell for now so we can see what's happening here, as well as the stage. And we'll pop those in when we want to reference those for our loudspeaker locations and stuff like that, and the structure as well. Alrighty, so before we insert loudspeakers into a MAPP file, we need to define where the listeners are. And the most basic way that we do that are with geometry. And in our primitives, we have some kind of preset shapes to just insert into a MAPP 3D model that can get you going very quickly. And the most basic version of that is a simple rectangle that would be, say, the floor of a flat floor auditorium or something. So I'm going to insert a rectangle by clicking that primitive. And the very first kind of tip that I will bring up in MAPP 3D is when you are in a perspective view, like the one we're looking at, one of the challenges of 3D modeling is where in 3D space you are inserting things. And the way we've tackled that in MAPP 3D is unless you're looking at a pure side view, you are inserting things onto the XY plane with a Z value of 0. So I'm just going to click with my cursor somewhere in front of the bowl, and it'll insert a rectangle right on the XY plane, right there. And in my Properties tab, I can see the properties of that geometry I just inserted. I can see I just barely missed right on that Y-axis, so I can change that to 0 right here. And we have dimensions and width of this rectangle. If it were 3D, we would have a height as well. And I can use the arrow keys to quickly change the size of this right here. So that's a geometry, but it's not defined as a listener plane quite yet. So if we go up to our object settings tab here, we can see some more detailed options of that geometry. We can change the layers, we can see the faces, but the thing to note here is the prediction checkbox. I'm going to predict or check that, and it will define this surface as a prediction plane, and that turns it kind of a purple color. We have an offset value here. So this is useful. I placed that rectangle on the ground, but that's not where people are. We want to define a listener ear height, either standing or seated. I'm just going to pick a seated ear height of about 1.2 meters. And you can see that purple plane levitated off of that rectangle. So that gives me where people's ears are. And one other useful thing is this through checkbox. So when we insert loudspeakers with center lines, we can uncheck this through box, and that will stop the center lines at the listener plane, which is a useful visual indicator that our loudspeakers are aimed at the people, right? And that will turn that original geometry pink. So at its most basic, that is a way to define a listener plane for MAPP 3D. Getting a little more complex, let's model the bowl here. We can see that it's three-dimensional and curved. So one way that we have set up to do that pretty easily is the angular extrude function. So one useful tool we have is called the snapping tool. I'm going to right click and select the snapping tool, and you can see my cursor highlights midpoints and endpoints of the SketchUp file that I imported. I'm going to go over to my pencil tool, the free draw tool right here. And so now when I draw, I can snap to the geometry that I've imported. So what I'm going to do is I'm going to trace a line, that a multi-segment line that defines the profile of this geometry. So I'm going to start at the middle, and I'm going to go to the first row right here, and I'm going to pick my last row. And once I hit enter, that will finish that line segment. Alrighty. So now to angular extrude this, this segment, I'm going to go to my modifiers, and I'm going to pick extrude. I'm going to go to angular extrusion. And one thing I noted that I forgot to mention on this was my center point that I want to extrude around. And from my memory, I saw that that was 7 meters on the X and 0 on the Y. That's where I want to rotate this extrusion about. And it's pretty easy to see right here. I have 180 degrees of rotation to do. So I'm going to type 180 for the angle, and I'm going to pick 7, 0 for my center of rotation. And I'm going to hit apply. And it swept, it did a sweep with that profile around the audience area and met that very nicely. So just like that rectangle, I'm going to go to my object settings, and I'm going to define this as well as a prediction area. I'm going to offset that at a seated ear height, and I'm going to make sure center lines don't go through that so I can see where my loudspeakers are aimed. All right, I'm going to turn off snapping mode. And let's see, we have our audience planes defined. So let's turn our stage back on, and let's put some speakers in. Okay, so I mentioned when we're in a perspective view, and this also applies to top views, we snap to the XY plane with Z equals 0. If you go to a side view, such as the left view, which I'm going to pick here, that gives us a nice elevation or section view. When you are in a side view, we are now snapping to the plane that we're looking at. You can tell by that there's a grid on the XZ plane that when I insert something with this view, it will snap to the XZ plane with Y equals 0, which would be something on the center line of this model, for example. So if I just right click right here and insert a loudspeaker system, it's going to be my center channel at Y equals 0 on the center. So let's insert a 8-box Lena array. default is 12 boxes, so I'm going to remove 4 of these boxes and hit OK. These options should be familiar if you're familiar with MAPP XT. We also show the power draw in those boxes as well. All right, so we have an 8-box Lena array. And just to show, I didn't aim this array. I didn't enter any rotation or splay angles to it. And if I right click, I can show center lines, and that will be pretty easy to see that I'm going to completely miss my audience with that default setting. So the first tool for arrays that's super useful and handy is the auto splay. So I'm going to go to Tools, Auto Splay, and it defaultly selected that loudspeaker system that I have. And I have 3 options here of the planes that I've inserted, and it defaultly doesn't pick those for me. I need to come in and define which planes I want to point those speakers at. So I'm going to start with the top of the bowl, the face 2 of that. And I'm going to go to face 1, and I'm not going to try to display this array at that rectangle. That might be too much vertical to cover with that. And of the 8 elements, I need to define which boxes go to the top of the bowl and which boxes go to the bottom of the bowl. I'm going to pick 6 and 2 here. And we also have settings that carry over from MAPP XT, like aiming factor and the splay limit targets that we have for this auto splay. I don't want anything to be super small, so I'm going to at least do a smallest splay of 1. And I'm going to move this box so we can see the center lines. And let's see if this works. I'm going to hit apply. And lovely, that splayed that array nicely along that vertical plane we need to cover. And once I rotate out of 3D, we'll be able to see how that is dividing that array on the listeners. All righty, so we have our loudspeakers, we have our listeners. I can move on to predictions unless there's any questions.
Doesn't look like we have any questions so far.
Alrighty.
I do want to point out that the angular extrusion tool was very nifty there to get that geometry to work in that 180. There's a lot of other 3D modifier tools in MAPP, especially getting into geometry, things like that. Alex actually was featured in some great YouTube videos. I think Matt has a link that he'll drop in the chat if you have more questions about building geometry within MAPP 3D.
Thank you. Okay, so let's just do a prediction right now. Let's look at 1 octave around 4 kilohertz. I'm just gonna use the default settings, and let's do a prediction for this Lena array. And this will take 1 second to prepare and predict. Unless it hung right there, I'm not sure.
So while we're doing a prediction here, we had a question from David asking, are we saying that the 1 speaker system has adequate horizontal coverage? And we do not know that yet. And so that's actually what we're working on right now with the pressure map prediction.
Sometimes on screen share, my CPU resources get taxed a little bit. All right, so yeah, that was a good question, because that's what we're exploring here is how we're covering this audience area. So the default settings for this Lena array don't necessarily give me all the information I want. So one thing I want to show is the different ways we can show SPL mapping in MAPP 3D. So the easiest way to get to those settings is to right click, and we can set max SPL. So I'm going to move this window over here so we can also look at our prediction area and see how this changes that. So on this SPL meter right here, we are dealing with absolute SPL. This is if you had a meter and we're looking at 1 octave of 4K, you would be seeing this band gain at your meter. We also have other ways to show SPL that I'll kind of show some views of. But mainly with the absolute SPL, we have a defined peak or max SPL on that. So right now the default is 110, which is pretty loud, right? So I'm just going to bump that down 10 dB. let's do 100 dB and hit apply, and we'll see everything get a louder looking color, essentially. It's not red or orange, but we can talk about different ways. SPL is shown here. One of the things that I find useful as a designer is not necessarily looking at the full resolution of the prettiest gradients and things, but more where my variance of coverage is, going from 0 to -3 dB to -6 dB from your loudest point. And we have some nice resolution options to show 3 dB or 6 dB per color, for example. So I'm going to turn that on, and you'll see things become more isolined and area defined with more solid colors. And that can make it a little more useful to see variance in, say, 3 dB increments is what I often look at. But with absolute SPL, we're still not necessarily seeing full 3 dB ranges that are clear of what the loudest point in the model is. We can kind of see just this lighter or louder green popping in here, but that's not necessarily a full 3 dB of SPL range. That's probably just popping up a half dB or 1 dB above the lower color of range. So a good way to see your variance from the loudest point on that listener area is the attenuation view. And this is actually what MAPP used to show SPL as when it was showing everything except 1 meter around a loudspeaker. You'd see the loudest thing that loudspeaker did and how that reached the listener. So we have the option to see that here, except now it's not in the air, it's on the listener plane, which is honestly more useful. You can certainly draw things to see what's happening in the air, but just at the listener plane, this is a really useful view to see your SPL variance on your listener plane. So that's a nice 3 dB per color attenuation view. We can go up to 6 dB, and we can actually change the range of this scale as well. The default is 42 decibels. But one trick that I like to show my team is reduce that range as low as you can go. Right now, the lowest we can go in MAPP is 12 decibels. So if we have 12 decibels we're looking at, and we're looking at 6 decibels per color, we're really only going to see 2 colors until we fall off the cliff. And 12 decibels down is essentially needing a whole new speaker to cover that area, is kind of the way I see this as a pass-fail SPL view. So if I hit apply, it'll bring in the crimson and blue view. And I can see just with the 6 decibels of variance I have, my array covers a good portion, but not the whole side of the audience area. So as a loudspeaker designer, I'd be thinking, all right, I'm getting 70% of my audience area. I need to bring in some side fills to fill in that area. So I'm going to go back to the absolute SPL view and 3 dB per color. And let's put a side fill in. So I'm going to use the same technique that I inserted the array with, going to a side view. And I'm going to pick the elevation where I want that side fill loudspeaker. So I'm going to pick somewhere down the shell, hoping I can mount this to the shell. I'm going to insert a loudspeaker system. This one's going to be an individual loudspeaker. And let's see if an X22 can provide a similar SPL to that Lena. And we'll see if that can keep up with the Lena, or if we should be thinking about a bigger loudspeaker.
And Alex, before we move on here, I wanted to mention in MAPP 3D now, this is the same window that you would insert in an individual loudspeaker or an array or a ground stack speaker. It's all from the same menu now. Is that correct?
That's right. Yep. We have a drop down at the top left that lets you pick your type of loudspeaker system you're inserting. And we have the gradient flown subwoofer array tool. We have point source for like JM1P arrays. So yeah, that's all in the same insert loudspeaker window now. Okay, so I've defined with my cursor where I want to insert this speaker in this XZ plane. And I can do all these positions and reference points in this window, or I could go to the object settings, but there's another tool that will help you quickly put loudspeakers in there and place them in your drawing much quicker than going through these windows right here. So I have my X22 right here. Let's go to a top view. And as we know, when we look at a side view, we are bound to a single plane. So I still have that X22 selected. I'm going to go up here to my top right and express settings. So that lets me view the model, but modify this loudspeaker that I have selected right here. So you can see the position values and the Y equals 0 since it's on that center line. I'm going to change that Y value with my arrow keys and just bump it up and move it in my model to about the edge of that shell. There we go. And we can also change our aiming. So this is often how I'll place loudspeakers and aim them, is with these express settings. So if I want to pan that loudspeaker out, I'll use the Z because I'm going to rotate around the Z axis. So let's say 15 degrees of pan on that loudspeaker. And we want to also tilt that loudspeaker down. So the Y value for rotation is tilt. I'm going to enter a down tilt, let's say 20 degrees. And since I have the through checkbox unchecked for this listener plane, that stops that center line. And I can easily see that I'm aiming that side fill in approximately the right location. But let's find out if that's the right location with a prediction. So I'm going to hit predict. We're going to predict both the array and the side fill.
Alex, while that's happening, you mentioned before that in express settings, you could use your up-down arrows, for instance, to move position or even rotation. Is that correct? So you can kind of see the center line moving. Is there a way to set the increment at which that goes?
Currently, it's in 1 degree increments.
Okay.
In future versions, we're hoping that that can be maybe shift modified to be decimal increments or something.
Sure.
But currently, yeah, that is in 1 meter, 1 foot, or 1 degree increments currently.
A lot easier than typing random numbers and hoping that it ends up on the right plot.
That's true. And I guess right here, I can demonstrate that arrow key adjustment too, because we can kind of see I'm getting a similar SPL, but I can slightly see a gap between my array coverage and my side fill coverage. So yeah, that's a good opportunity to change that pan and bring it towards center a little more. I'm going to decrease this panning with my arrow key, and let's say 11, 10 degrees, something like that. Cool. So I have 1 side fill, and I could insert another speaker and duplicate the settings. But one easy way to do that in MAPP 3D is to select a loudspeaker, and we have a mirror tool. And that's these 2 triangles in your tool settings pointed at a center line. And we can click the mirror tool. And we have 3 options of the direction and the axis that we want to mirror that loudspeaker. We want to mirror it along the Y axis because this Y, the green axis, is crossing our center line. So we want to flip that from right to also left of the house. And there we have 2 side fills, and we could do a prediction to see the full coverage. But just for time, I'm gonna move on, and we'll show some more predictions that show SPL headroom when we get into the measurement view. With this system right here. All righty.
We do have a question from Palmer going back to the pressure plot predictions. Asking about the color variations. He asks, are the color variations 3 and 6 dB or is it something else? Can you just go over that real quick again, Alex?
Yeah, we have a few options for that. We do have 3 and 6 decibels per color to show. We can go down to 1 or a half decibel per color, or the full resolution, which is a gradient between red and blue.
Palmer, what we were showing before is that by doing a 6 dB per color, you're able to create that variation line to see kind of broader coverage rather than the full resolution.
Cool. So we have our loudspeakers. They're covering pretty well. Let's get deeper and find out the full frequency response as we would on site with microphones in the seats. So let's go to our left view once again. And the same way I inserted loudspeakers, I can insert microphones. So I'm going to pick somewhere on the flat center area, and right click and insert a microphone. So once again, this is bound to the XZ plane for now, and it has a Y value of 0. That's fine with me, and it's right where I clicked, so I don't need to define a height or anything. I can just kind of trace my listener plane that's already offset to seated ear height, and that lets me basically drop mics where I've defined those listeners already. So let's put 3 microphones in here. And 1 more. Let's put this last mic at the top. All righty. So we have 3 microphones. Let's go to our measurement view. So if you've used SIM or SMART or any 2-channel analyzer, this should be very familiar. We have a new way of showing it in MAPP with a quadrant view, where we can see the impulse response, the resultant phase and amplitude, as well as a room plus a processor trace. We can make these windows full screen, but let's stay in the quadrant view so we can go through the different functionality of this. I can pick my processor channel, my microphone. I can do smoothing on my traces, which can be useful. And I can pick my time window, or if I want my processor trace to be inverted. But we also have our auto set delay, which everyone should be familiar with if you've used an analyzer. We can see our impulse. We can see how long that took to get to the microphone, but it also makes our phase trace, not very readable. So if we auto set that propagation delay, that gives us a more viewable phase trace, as well as aligns that first impulse, loudest impulse, to the 0 time. And we have, like SIM, 4 recallable trace memories, as well as a live trace to see. So I'm just going to walk down my microphones. I have mic 3 here. I'm going to store that trace and save this. I'm going to go to mic 2. And I'm going to store this trace. I'm going to set my delay first, though. And I'm also going to go to mic 1, and I'll leave that one as the live trace. So as I stored those traces, those populated into the memories that we can view down here. If I turn these on, we can compare the 3 microphones that I inserted and see I have a relatively consistent trend in my frequency response, and the phase response kind of confirms that we're looking at the same system. And also in this impulse response, you can kind of see which microphone is getting some of that side fill compared to the other ones. So you can see a lot of data in this view. And that's a really great way to look at your overall system response, but it's not showing necessarily SPL headroom. We have a different tab for that. We can go over here to the headroom tab, and this gives us a way to look at SPL headroom that our system is doing, and a few new things that we've modeled when we rescanned our loudspeakers for MAPP 3D that's pretty awesome, I think. So we're looking at this view, and we see a similar 3rd octave graph right here of our frequency response. And we'll see down here, we still have our trace memories as well as our live trace. And as we move over, we start to see the SPL values that those microphones picked up with this system at its current level and processing. So we have our average SPL A-weighted, C-weighted, and unweighted right here. And then we have a linear peak SPL, which typically is 12.5 dB above your average, because that's the crest of our peak noise that we measure our speakers with. And there's a new field here called maximum peak, linear peak SPL. And I have a few things to talk about before we talk about that one, but just note that it's a lot higher than the linear peak SPL. But before I talk about the max linear peak, I want to talk about this table right here. So in this table, we'll see all the speakers that got predicted for this measurement. We see their names and we see the output channel, but in the middle, we have a delta decibel column. And to explain what that is, when we scanned our loudspeakers, we not only scanned their dispersion on every angle we could and the SPL, but we also measured the input card's sensitivity to input signals. So in MAPP 3D, we're essentially emulating a full signal chain from a signal generator through a processor, out of a loudspeaker, through the air to a microphone. So that's the full signal chain propagation that we can emulate in MAPP 3D. So the thing to note about this delta decibel table is when we measured the input sensitivity of the loudspeakers, the way we've scaled our product line leaves some headroom left over to push it past 0 dB on the input to that loudspeaker and still get some linear headroom out of a lot of our products. So what we can see from this delta decibel table is the yellow and green mean we have headroom to still push this system farther if we wanted to, and that's what we're going to do. So this yellow right here, since it's different, I can just tell that that's that side fill loudspeaker that's getting to this microphone. And we have the 8 boxes of the Lena array. So if I turn my generator at the top left, let's turn it up 2.2 decibels. And that moved everything into the yellow, but now I can see on that X22 loudspeaker, I'm hitting the limit of that loudspeaker, and that's the limiter kicking in, and it's probably not going to give me much more SPL that I would consider usable for the system. And then the Lena array still has 3 decibels left over. So even just from this table, I can see that my Lena and my X22, my Lena can go about 3 decibels farther in headroom than my X22. And as a loudspeaker designer, that might be the point when I say, okay, the X22 is not going to keep up if I'm really running this system to the limit. Maybe I should consider an X42, for example, the next size up. But we can move this even farther up and maximize the Lena. But what you'll notice is this linear peak is also going up as I increase the SPL headroom. So I could keep adding 3 decibels to this, but one thing that I do to check my overall SPL headroom of a system and push it as far as I can go, when we put the generator into MAPP 3D, we made it possible to do 50 decibels of positive gain on that generator. Way more than any loudspeaker headroom will have in it, but often I'll just type in 20 decibels to completely max out every loudspeaker in my system. And that lets me really compare SPL headroom of products at their limit. And if you're familiar with MAPP XT and how that showed SPL headroom, when we scanned the loudspeakers for MAPP XT, those were at limit. So this is basically going back to MAPP XT's way of showing SPL headroom of the product's full potential of SPL. All righty. So now we can see everything's in the red. We're pushing it all the way we can go and still be linear in our SPL headroom. So I can see from the system at this microphone, I could get 96.6 average SPL with A weighting. If I'm shooting for the highest number possible to fit in a tender or some kind of quote or bid that I need to hit a huge SPL number like a stadium or something. This is the max linear peak number is what you're going to look at, because that takes into account both the SPL headroom in the sensitivity of the loudspeaker, but it also takes out phase in this equation, which lets us just get the highest number possible as if you were, using an RTA in free field, basically. It's the highest theoretical number that you can get out of a system while still being linear. So that's the 119.9 number that at this mic position we can get. And going back to predictions, we talked about how the X22 wasn't quite keeping up with the Lena when they were maxed out. We can also view that in our SPL. Let's go to a top view. Get out of the selection mode. There we go. If I predict this with my headroom maxed out, what we should see is about 3 decibels difference in our prediction pattern. So I have plus 20 on my generator. I'm predicting all the loudspeakers, and we should be able to tell on the side fills that just from counting colors that we're about 3 decibels lower than our Lena arrays covering in the center. Yeah, Zoom really hit my CPU when I started sharing. So there we go. If we're talking yellow and peaking into orange for absolute SPL, we can see their side fills, are about 3 decibels down from where we're talking in our main area. So depending on the show, if you're comfortable that this isn't going to hit the top of a Lena array, you're probably fine with this. But if you really are running the system to the limit and riding the edge, the X22 might not keep up. So that's one way to see how products compare in MAPP with SPL headroom, popping mics in, and measuring a system as you would in the real world. And since we've emulated that input sensitivity, this should match as close as possible to the real world with the full signal chain.
That's great.
Cool. So that's my high school course on inserting loudspeakers, geometry, and looking at measurements in MAPP 3D.
That's great. I want to remind everyone, please submit your questions through the Q&A. Alex, can you tell us a little bit about electrical consumption and how you can see those numbers for your different arrays?
Absolutely. So let's look at the Lena array. And let's go to the object settings right here. So when we're looking at the object settings of a loudspeaker system, or when we're inserting this, we can also see this, is we have a few tables down here that show the rigging and array positions that were also in MAPP-XT, but a new one is the electrical consumption down here. And we have the totals and the totals plus 30% safety factor for the voltage I've set up for this. And so I can see 18.4 volts at 115 for this 8-box Lena array. And also for the full system that we've built in our model view, at the top right, we show the total SPL, or sorry, the total electrical consumption of that system. And this is where you select your voltages for that.
Does changing the voltage, the operating voltage of the speaker, affect the SPL prediction at all?
Nope. Nearly all of our loudspeakers can accept 100 volts to, I think it's 250 volts, but it might be 230. But yeah, they have switching mode, so that does not affect the performance of the loudspeaker. And so changing voltages should not change any prediction. It's really just that electrical consumption calculation.
All right. I've got a couple more questions for you here, Alex.
Okay.
You mentioned before using your top view or side view to snap to a plane when placing geometry or loudspeakers. Would it be easy to, for instance, look at a side view, and if you place an object in a top view somewhere along the Y axis, when you switch to the side view and move it around, would you stay to whatever Y point that you were snapped to before? Does that make sense?
That's correct. Yep. Yeah. So that is something I do often is insert something where I know in plan view that loudspeaker needs to go. And I guess that can be a good demonstration of just dragging loudspeakers around. So I'm going to insert a new loudspeaker here on the XY plane. And let's say I may miss that. I can grab that orb and move it to where I want it. And then if I go to a left view, I can do the same in the XZ plane and bring that up to the elevation that I need. So you can see that loudspeaker down here is stuck in the ground right now. So if I pick that loudspeaker, I can grab his orb and move him vertically. Maybe. Thank you, Zoom, for taking all my CPU. There we go. So yeah, that's
Great.
a quick way to move loudspeakers around, bound to planes, while maintaining where you put it in plan, and then just 3Dify it in the Z-axis.
Sure. All right, so we've got a couple more questions here. Ziad asks, when you mirror an object and later change the original one, would the mirror one follow? So is there any kind of linking option for the mirroring?
Yeah, there's not currently any linking. That is a feature that I've requested, but yeah, that is something I'd like to see is having linked symmetrical loudspeakers.
Sure.
There's a lot of things that would be nice to have symmetrical, like free drawing an audience area. You don't have to do half of it. So yeah, that's one thing that that we would like to see added in future versions. So it's a good
Great.
question.
Good question from Palmer here. Is there a way that you can insert an obstacle like a balcony within MAPP 3D?
Yeah, so that is, that is the dream, right? Of having a full acoustic simulation where we
Sure.
can model occlusion, absorption, all sorts of actual acoustic properties of things. But at its most, basic premise of MAPP 3D, we wanted to do a loudspeaker prediction software and not necessarily do full room acoustics, because that's a lot of math and calculations, because sound isn't necessarily like light, where if you put something in front of it, it's completely stopped, right? You can be under a balcony, out of the line of sight of a loudspeaker, and a good amount of low frequency is still going to get to you. And the question is, how do you do all that math for any shape or anything we put in a
Sure.
software? So that's definitely something we're going to work on in the future. But to get the software out and to have people predicting loudspeakers and making good decisions, we stuck with the free field simulation. We have a ground plane that you can simulate like a ground or a reflection off of something. But yeah, as far as actual acoustic occlusion and absorption and refraction,
Sure.
that other people already do that and charge thousands of dollars for it. So our software being free, we wanted to get that in the hands of as many people as we could and get them using our loudspeakers as accurately as they can. And then we'll do the acoustic stuff later down the road. But yeah, that is something that everybody wants really bad.
Sure.
Definitely. So yeah.
Is there any tips for, especially for an under balcony, of understanding like soloing of different loudspeaker arrays to see, for instance, what an under balcony might have towards the back of a raked seating versus the main array prediction?
And are you talking SPL or like coverage?
Coverage, I guess, mostly.
Yeah, let's see. One thing that I do fairly often, it's kind of hard to illustrate in this specific model, is I'll use that 6 decibel variance that we looked at, and I'll pop one speaker in that I want for a distributed array, such as a front fill array or a under balcony array. And I will just do one speaker and find out how wide 6 decibels of coverage is at the listener plane. And as I make a uncoupled array of those loudspeakers, that 6 decibel coverage is what I want my spacing of loudspeakers to be. So once I find that width of 6 decibels of coverage, I can use the array tool in my tools up here. And I can say, all right, that was 4 meters wide of coverage. I'm gonna space my underbalks 4 meters, and then I can predict it and confirm that. But yeah, that's a quick way to just check your 6 decibels of coverage, and that is your resultant spacing often of loudspeakers. Once you get into angles and non-linear arrays, that doesn't necessarily hold true. But if you're just doing
Sure.
a straight line, that is roughly accurate to do.
Great. All right. So please, anyone, if you have additional questions, feel free to ask them in the Q&A here. I have a couple more questions. Maybe we can get back to different loudspeaker configurations that we can insert, including like a point source array beyond just line array systems. Can you show us some of the options there? I know recently some of the legacy systems have been added in as well. Like you mentioned, JM1P.
Yeah, so let's look at the different options. If we go to point source array system, this is a basic horizontal array that doesn't let you build in 2 dimensions. The endpoint source array will be more for the X40 and X42 family, where you can build bigger clusters, and that functionality isn't quite finished. It'll be in the next point version, hopefully. But just for a point source array system like a UPQ D2 or a JM1P array system, the similar functionality that was in MAPP-XT is also in MAPP 3D. So I can build up an array of 4 or 5 JM1Ps, and JM1P specifically has a fixed splay of doing a tight pack between those cabinets. So I can adjust the splay of the JM1P, but let's do a UPQ D2 for example. if I'm using the array plate of the UPQ D2 series, I do have options. And those options for picking different holes in that array plate are predefined for me in this. And that makes it easy to put an array together. And I can pick where I want the center of the reference point for that array. So if I pick the first cabinet, that's not necessarily going to let me tilt and roll the array easily. It'll be a little cockeyed and weird. So when you do an array like this, I want to pick the middle box of that system. So I'm going to pick the third box to make that center of the array the reference point. So tilting will be symmetrical at that center point.
Sure.
And let's see, other stuff. I can go through some other loudspeaker systems if
go
you
ahead.
wanted to see. Yeah, another one that's really useful is the gradient flown subwoofer array. So this is, basically an array of subwoofers, but we have some functionality built in there to insert the polarity reversal and the delay to get a gradient cardioid hang very easily in MAPP 3D. So we can pick our models here, like 900 LFC. We can pick predefined quantities of these that lend themselves very well to gradient cardioid settings, 3, 5 multiples, basically. So let's do a 6-box array. And down here, with the output channels defined, let's make these, say, 15 and 16. Oops. I can check here to add to existing processing of those channels. I can just hit OK. And then once I go to my processor settings, that polarity reversal and delay will be inserted into those output channels. So all the math right there.
That's great. And I think we can talk briefly about Galaxy and the ability now through MAPP 3D to sync these processor settings straight from the software to a Galaxy device.
Yeah, that's right. Let's see. I'm not sure if I'm set up to demo that completely right here, but we can go to Signal Processor Management. And if you're on the same network as a physical Galaxy processor, it saw my Galaxy in the rack over there. So I can select that device, Harbaugh, and I can connect the device. I have the option to push my settings from MAPP to the Galaxy, which I don't want to do on my home theater system, or I can pull the settings from the device and get my home theater calibration on MAPP if I wanted to. And once you are connected, that is a live control of your Galaxy. So you could design your system in MAPP and get it installed and then walk into the theater with your MAPP system, compass, and a Galaxy, and you can confirm that the loudspeakers were installed as you designed. You can take your processing that you set up in MAPP with predictions and things that you did on the road and send that to the Galaxy. And let's say the room was slightly different and you had to adjust your compass settings to accommodate the room, you could have that linked to your Galaxy and you could save that MAPP file with those Galaxy or compass settings. So it's something that's really handy to have those interlocked and controlling each other live. So
that's great.
I guess I'll risk it and pull my settings.
One more question that I have on the Galaxy and back to the measurement view. We mentioned before using the inversion of the signal, so you could see the inversion of a Galaxy output. For instance, for an EQ, you could see how that is being applied specifically to a microphone in this case. Can you talk through that a little bit?
Yeah, I guess it's fortunate that I brought in some EQ settings to my Galaxy now.
There you go.
So
yeah.
if we just look, if we just look at a trace of our microphones in the model, it's not going to be EQ to what we wanted to do. But let's pick an output channel such as my left screen channel, or a different one. right there. So for my sub of my surround based management, I have essentially a high pass filter made out of U-shaping. And with this trace right here, the green trace, um, that's not necessarily what a high pass filter is doing, right? Or a low pass filter, I should say. Sorry about that. This is what it's actually doing. But if you're looking at a trace and you see a frequency that you want to tackle, it can be very useful to have your processor trace inverted, and you can align your, you know, filter to the bump in your uh, analyzer trace. And that can be a very easy visual indicator to say, hey, I saw this bump and I put a filter in to fix that bump, and then you'll see the result be those combined, essentially. So, yeah.
That's great. Going back to the Galaxy Link question from Palmer, once the two devices are synced, do you need to manually resync after you make changes, or all the changes in real time until you disconnect?
Real time. And let me see if I can demonstrate that. This might take a second for Compass to load, but yes, you can have Compass and MAPP 3D next to each other and change one thing and it shows up in the other.
That's
so,
great.
Yeah. This
So
might
it does
tax
allow
my
you
system
to,
with a Zoom screen share. So
sure.
sorry if I can't
No worries.
can't get that going.
But yeah, so in my imagination, it allows you to design the system here in the software, get it up and running in the venue, and not have, connecting the design and the implementation phase together, through the Galaxy, and not having to have two separate softwares.
Absolutely.
There's still tools in Compass that make the Compass the better tool for live connecting to the Galaxy and manipulation of settings. Is that correct?
Can you repeat that? I'm sorry.
Sure, yeah. Compass would still be the better tool to manipulate the Galaxy settings in real time, maybe setting matrix values, things like that, rather than doing it through the MAPP 3D software.
Basically, yeah. What we're emulating on a Galaxy processor in MAPP is just the output section. So we are essentially taking a generator and molting it to all the outputs and then emulating the processing of that. So what you're not going to get in MAPP as far as the full Compass functionality are, your input processing, your matrix, both, summation and delay matrices. And some things are just really handy in Compass to do in the site. Either Compass Go, like linking channels together, more user functionality that is kind of built in Compass to be on-site stuff. Isn't quite done in MAPP 3D. Those are all things that we're looking to do down the road. But yeah, so just like this, if I change this to 66 hertz, oops, that's not what I'm doing here. Let's change a U-shaping filter. If I just change this one, you can see MAPP is also changing that EQ curve.
Wow, that's great.
Yep.
Even with Zoom and the lag.
Even with Zoom, even with the screen share running.
Yeah. Well, that's great. So I'll open it up just if there's any last questions, feel free to get them in here. We're just about ending up here at 4 o'clock. Alex, is there anything else you wanted, any cool tips or tricks last minute you want to toss in here?
I have a bunch of webinars and roundtables that we did for MAPP 3D. They're on YouTube. If you just search for MAPP 3D, they'll probably come up. I believe we have a playlist that we can link in the chat. But that definitely, we looked at, say, a high school, what I call my high school course of MAPP 3D, but I have trainings for undergrad and graduate level of doing more complex geometry, such as my cookie cutter technique, and a lot of other things on those roundtables that aren't just for me, but from Bob McCarthy and Merline, that really help you get going into the more advanced features of MAPP 3D, because we probably, we just got you running in this tutorial, but there's a lot more advanced features to dig into for the system designers.
Sure. And we've got one more question from Palmer, which I think we can just address here before we head out is if you need any assistance, if anyone needs assistance with a design, TC Furlong and the Meyer Design Services are happy to help out when it comes to designing Meyer sound systems.
Absolutely. We're
Yep.
here to help.
So I think on that note, we can wrap up. Alex, thank you for your time today. This has been very helpful.
No problem.
Thank you for everyone for joining us here today. As I mentioned, we're going to be putting this on the recording of today's webinar on our YouTube page as well. So we'll make sure to send a link of that out to everyone. As a reminder, MAPP 3D is available currently on the Meyer Sound website for free download. Go ahead and download it on your computer, poke around. If you have any questions, feel free to reach out to TC Furlong. We're happy to help with that. I do want to make an announcement that we have our next webinar in the series scheduled for April 27th. We're going to be meeting with Sound Devices to discuss their MixPre 2 series. So there should be a sign up for that link in the chat here. We'll also link that in the follow-up email. Hope everyone can join us over there as well. Again, a big thank you to Alex for your time here today. And a thank you to Matt Calera, who is helping us out with the TC Furlong webinars. Always great to have you, Matt. If you do have any questions, feel free to email our team here at sales@tcfurlong.com. There is also an exit survey that will be linked as you leave the webinar here. Feel free to drop us a comment if there's some future webinars you might want to see here with MAPP 3D or anything else. And we'll make sure to reach out once the webinar is posted on the YouTube page. So thanks again for everyone coming, and thanks again, Alex.
Thanks, everybody.